Now we are going to give a few important results on the conditional expectation. Some important results on conditional expectation. First important result, expectation of x given the random variable takes a value small y is the value of the random variable expectation of x given capital Y. So sometimes we write this in the form of expectation of x given small y. Either we write like this or we write expectation of x given small y, that is a value of the random variable expectation x given y. The second result, the expectation of x given small y is always going to be greater than or equal to 0 whenever the random variable is going to be greater than or equal to 0. That means whenever the random variable takes a values greater than or equal to 0, or the probability of x greater than or equal to 0 is 1, in that case the expectation of the conditional expectation of x given other random variable is also going to be greater than or equal to 0. The third result, if you compute some constant given the other random variable, that is always going to be 1. Next one, if two random variables are independent, if two random variables are independent, then the conditional expectation is same as the expectation of that random variable. Because these two random variables are independent, we can prove it. We can prove it by considering both the random variables are discrete, both the random variables are continuous. You can easily prove it. That means that is, suppose I consider both the random variables are of the continuous type. That means expectation of x given y, that is nothing but minus infinity to infinity x times conditional is same as joint divided by marginal. Again, since these two random variables are independent, I can rewrite the product of marginal, and it cancels out. So you will get minus infinity to infinity x times the probability density function of x, that you know that is same as expectation of x. Here I have considered both the random variables are continuous type random variables. Even if you consider both the random variables are of the discrete type, again you can prove it in the same way. So if two random variables are independent, then the conditional expectation is same as the original expectation. Next result, suppose you go for finding the conditional expectation of some constant times ax plus p times y with the other random variable z takes a value small. That means now I am considering three random variables x, y, z. So expectation of some constant times one random variable plus constant times another random variable given the third random variable takes some value that is same as constant is out. So expectation of x given the random variable takes a value z plus constant is out, the conditional expectation of y given z takes a value z. So this is true for all a and b both are real. This also can be proved. The sixth property, I said expectation of x given small y is a value of the random variable. Therefore, you can go for finding expectation of x given capital Y. Expectation of x given capital Y, that's a random variable. We are finding the expectation for the conditional expectation. That means you can prove it. You can prove it for considering both the random variables are discrete and continuous. So let us prove it, then we will write down what's the answer. So the left hand side is going to be minus infinity to infinity. By considering both the random variables are of the continuous type, that is expectation of x given this value multiplied by the probability density function of y. By using the definition of conditional expectation, we can expand. So the outer one is minus infinity to infinity f y dy. Now I am just expanding what is the conditional expectation of x given y. That is nothing but minus infinity to infinity x times the conditional probability density function of. So this is inner integration and outer integration is minus infinity to infinity f of y dy. That is same as, now I can expand the conditional probability density function, that is nothing but minus infinity to infinity x times the joint probability density function divided by marginal probability density function, and I can rearrange the probability density function dx dy. So I can cancel these two, and also I can use minus infinity to infinity x times, so I can take it out, minus infinity to infinity x integration of minus infinity to infinity f of x comma y dy is nothing but the probability density function of x. Minus infinity to infinity integration joint probability density function with respect to dy, that is nothing but the probability density function of x, then dx. That is since minus infinity to infinity joint probability density function of x and y with respect to y, that is going to be probability density function of x. So this is nothing but expectation of x provided it exists. That means the expectation of x given y is nothing but expectation of x. This is a very important result. The left hand side involves the random variable y, whereas the right hand side is free from the random variable y. That means If you want to compute the expectation of x, we can always find another random variable. For that random variable, you find out the conditional expectation of x with respect to the sort of dummy random variable. After finding the conditional expectation, you find out the expectation of that conditional expectation, that is going to be the expectation of x. That means you can choose any random variable y as long as the conditional expectation you can able to compute. Then find out the expectation of conditional expectation is going to be the original expectation. So this is a very important result. Whenever it is very difficult to find out the expectation of one random variable, but you can always relate that random variable with another random variable, then compute the conditional expectation. If that process is easy comparing to finding the expectation of the random variable, then you can use this result and find out the expectation of the random variable x, that is same as expectation of conditional expectation x given y. So we are going to use this property to compute the expectation for a random sum. If you recall, we have discussed the random sum long back. That is, we have used s suffix n as a random sum as a sum of n random variables, where n is a discrete type random variable. N is a discrete type, in particular it is a positive integer valued random variable. So if you want to find out the expectation of s n, that is nothing but expectation of s n given n. That means first you fix the value of capital N, then find out the conditional expectation, then compute the expectation for that. That is nothing but, since we made in the random sum problem, we made the assumption of xi's are independent mutually. Xi's are IID random variables. Xi's are IID random variables, as well as n and xi's are independent. Therefore, you can compute that is equal to expectation of n multiplied by expectation of x 1. All are IID random variable. Therefore, any one random variable expectation of x multiplied by the expectation of n, that is going to be the expectation of the random sum. We have already discussed the random sum much earlier. Now, in that time we have discussed only the distribution of the random sum. Now we are discussing the expectation of the random sum, that is same as expectation of n multiplied by the expectation of x1, since all the xi's are independent random variable. This is called Wall's equation. Using the earlier property, we can find out the expectation of the random sum is the product of expectation of n with the expectation of x1. The next property, property number 6, expectation of, so this can be extended for a function of random variable. Expectation of h of x also can be computed in the same way. Expectation of conditional expectation of h of x given the random variable y, as long as h is a Borel measurable function. Therefore, h of x is a random variable. So the expectation of h of x is same as expectation of conditional expectation of h of x given y. That means we are extending the previous result with the function of random variable. The seventh result, expectation of x times h of y given y that is same as h of y expectation of x given y. X multiplied by h of y given y takes a value small y, that is same as h of y into conditional expectation of x given y takes a value small y. That means when you made it given y takes a value small y, the h of y no more random variable. Y is a random variable. H of y is a function of a random variable where h is a Born measurable function. Therefore, h of y is a random variable. So, when y takes a value small y, h of capital Y is no more random. It's going to be treated as a constant. So, constant is out while computing the expectation. So, h of y times the conditional expectation. There are some more properties with the conditional expectation, that is with respect to the sigma field and so on. So, for this course we stop it with this many results. Now, we will go for the next topic is called conditional variance. The way we discuss the conditional distribution first, then conditional expectation. So, now we are going to define the conditional variance. That is nothing but variance of, we are going to define conditional variance as the variance of x given the other random variable takes a value small y, that is same as, it is similar to the variance formula, but now it is a conditional variance, that is same as expectation of x square given y takes a value small y minus the conditional expectation of x given small y the whole square. When you compute the variance of x, that is expectation of x square minus expectation of x whole square, the same way one can define the conditional variance as a variance of x given y takes a value y, that is nothing but the expectation of x square given y takes a value y minus conditional expectation of x given y. We have already given the result for conditional expectation of h of x. So, now we are going to find out the variance of the random variable x using the conditional expectation and the conditional variance, that is a variance of conditional expectation plus expectation of the conditional variance, provided the second order moment that is finite. So, the way we are finding the expectation of x using the conditional expectation, one can find the variance of x also in terms of the conditional expectation and the conditional variance. That means for any random variable, variance of x can be computed by finding the conditional expectation and the conditional variance first, then apply the variance and the expectation in the vice versa, then summation becomes the variance of x. We are going to use this result to compute the variance of random sum. That is, random sum is defined sum of IID random variable, and n is a discrete type positive integer random variable which is independent of x size. So, we have already got it the expectation of Sn, that is expectation of n multiplied by expectation of x1. Now, we are going to find out variance of the random sum using the previous result, that is going to be expectation of variance of the the conditional expectation of Sn given n takes a value small n plus the expectation of the conditional variance of Sn given n takes a value n. So one can find the variance of random sum using the conditional expectation and the conditional variance, computing the expectation for the conditional variance and variance for the conditional expectation. That sum quantity is going to be the variance of random sum. We have already the results for variance of expectation of Sn given n takes a value n. That is nothing but the variance of the expectation of Sn given n takes a value n. That is nothing but expectation of finite n random variables expectation. That is nothing but n times the expectation of x1. Since they are identical, you can make it n times expectation of n. That is same as since you are going for variance of n expectation of x1 you have to treat it as a constant. So when you are computing the variance of n is a random variable here and this is a constant, therefore expectation of x1 that whole square multiplied by variance of n. Okay. So this is a one quantity for a variance of conditional expectation. So we got variance of expectation. Now you have to go for conditional variance, then you have to go for expectation. So first we have to find out variance of the conditional Sn. That is going to be when n is fixed. So you are trying to find out the variance of finite n xi's. That means all are independent random variable, therefore it is going to be n times variance of x1. Therefore the expectation of conditional variance, so that is same as expectation of n variance of x1. Variance of x1 is a constant, so constant is out, so that is variance of x1 expectation of n. Therefore adding both the quantities, variance of Sn is going to be, the earlier answer is it is expectation of x1 square variance of n into variance of n plus the second quantity is variance of x1 times expectation of n. So this is going to be the variance of the random sum. So once you know the distribution of xi's and distribution of n, one can find the distribution of random sum, and if you know the mean and variance of xi's and n, you can find out the mean and variance of the random sum also.